Okay, so welcome back. Part two of the Copolymer story. It's going to be presented by Professor An-Chang Shi from McMaster University.
Yeah.
Okay, great. Very welcome to have you.
Yeah, thank you. Yeah, thank you very much, and also thank you everyone for sticking around to listen to these Prof Copolymers. And I really appreciate Greg's talk earlier, which really laid all the background. So that's really good. Now, what I'm going to do today is to talk about instead of melt, which was what Greg mentioned. The emphasis of my talk is to talk about blends, and the blend, of course, mean you have mixtures of different copolymers. And the basic idea is very, very simple, is that Greg talked about the system doesn't like to have voids in the system. And then there's need to stretch polymers to fill these voids. But then the idea now is that can we put different components into these places? And that will help sometime the system to relieve these packing frustration, and then emphasize the interface effect, and that can lead to the formation of different structures, or enhance the ability of the system to form the structures we want. So that's the basic idea. Now, before I start, I'd like to mention that starting Prof Copolymer blend was a topic which I started as my first research project when I started at the Xerox, working with Young and Andy. And that's actually is a topic for me to learn about Prof Copolymer physics, because I didn't do Prof Copolymers at all before that. So, and we've been working, or I have been working on this topic for quite some time, and currently we kind of repeat it back and emphasizing this. Now, most of the work I'm going to talk about from Casper basis started with Dr. Mei Jiao Liu when she was a postdoc with me, and also Professor Wei-Hua Li. And currently, Tom Lei and Jia Yixue were the two graduate students mostly working on this project. Now, let me, well, probably should just skip this one because Greg talked about this. The idea is that copolymers are many, many different chains linked together. So that's a little different from the other, what we would call copolymer or heteropolymer, like a DNA or protein, because there you don't have blocks. And so the block simply means that you have one chain and another chain that link together. And again, there's an infinite number of possibilities to construct copolymer. And also, as I mentioned, in my previous talk, if you were here, if you wasn't here, I'd like to say it again. We like to talk about frustration, or use frustration as a key concept to organize the self-assembly and structure formation. And I would say block copolymers are intrinsically frustrated. That's because you're linking different polymers together, and they usually don't like each other. So there you go. So because of this, the self-assemble to form different domains, and the packing of these domains to form structures. That's Greg mentioned about quite a bit. Now, I'm a poor theorist, and the only thing I do is mean field theory. And so the good thing about block copolymers, or polymers in general, is that once the chain becomes long enough, then it becomes genetic, in the sense that the only thing matters is that it is the one-dimensional object, and there's some interactions. So that's that. Now, because of that, we can use different molecular models For example, we can use the textbook one, which is freely joined chain, just like you think about the segment is something like this, which can rotate freely in space, and you just simply join many of them together. And that's one model we use quite a bit. And the other very popular model is a continuum Gaussian chain model. And of course, you can, these models can go back and forth, depending on the non-scale you are looking at. Now, with this, so the theory we do is we start from this molecular model, and then we just write down the partition function or do the statistical mechanics of that. And of course, now the problem becomes a very messy one where you have many, many chains. Then the theory becomes simpler if you look at one particle or one molecule. And then you have one molecule interacting with many other chains. And then you can do not an approximation, but a mathematical transformation to transform these interactions from all the other chains into a background field. And you simplify the problem to one chain in the field. And that's a much simpler statistical mechanics problem, which we can solve depending on the model system. We have different ways to solve that. And then if you allow these background fields to fluctuate, there's no approximation. The theory is still exact. And of course, then you simply transform the one unsolved problem into another unsolved problem, which doesn't seem to be very helpful. But then the good news is that usually mean field approximation works quite well. So now if we minimize the free energy with respect to this background field, then that gave us an equation which determines the background field once the chain conformation or the chain distribution is determined. And then that leads to a set of equations which we can solve. So this is basically the equations we solve. And mathematically, I would say this is a set of nonlinear and non-local equations, which has many solutions. So that's that. And usually we formulate this theory in different ensembles, depending on the problem we are interested. For example, this formulation here is in the so-called grand canonical ensemble, which means the number of chains in the box is fixed. Sometimes this is not very convenient for plants. And for plants, the more convenient ensemble to use is the so-called grand canonical ensemble. So what that means is that the number of chains can fluctuate. And what's controlling the theory is the chemical potentials. So then you can just write down the free energy, the mean field free energy in terms of the chemical potential and the temperature. And then you minimize that. You get a set of self-consistent equations, and these are the equations we need to solve. And then the way we solve these equations is just using iteration. And you guess what the mean field should be, and then you solve the one chain problem, statistical mechanics problem. The equation here is for a Gaussian chain. For a Gaussian chain, this single chain problem becomes a diffusion equation because it's a random walk in space. So it's a diffusion equation. And another thing for the physicists in the audience, diffusion equation is of course analog to the Schrödinger equation. And there's lots of studies in quantum mechanics, and indeed quantum mechanics, many techniques in quantum mechanics can be transformed and transported into polymer physics. There's of course a lot of studies there, but we can solve this. Then use this chain conformation property, we can calculate the density profile. And once we have the density profile, we can calculate what the field should be, and then we can compare the field we guessed. And if we agree, we are very lucky, that's great. And usually they don't. And then you upgrade the field using a number of different ways this is where mathematics comes in. You can use the simple iterative method. You can use very fancy Anderson mixing method, which means you use many steps, information from many steps to predict what's the next step. And once you do that, then you just repeat this until things converged. Then you would have your solution, and you feed the solution to the previous formula for the free energy. Then you have the free energy for the structure. Now, the way we do this is we do this for all the structure we can handle. So that leads to another question, which actually alluded to when, during Greg's talk, which is that how do we know which structure we're going to use? And there, it is really related to this general problem, which what we do is really an optimization problem. And there are many solutions, all in terms of free energy landscape. It more look like this. There are many minimal. And you may have, well, there must be one global minima. That would be the equilibrium phase. And there would be many local minima correspond to metal stable phases. And the difficulty is that how do we know how many of them? And the answer is we usually don't. We have some idea, but we don't. And then for the theory part, the way we do this is that it depends on what we want to do. If the purpose here is to discover what structure could be, then that's hard, but it's not completely helpless in the sense that what we do is we just try many different initial configurations. For example, you can have random initial configurations with random different randomness. You can have a random configuration in real space, a random configuration in Fourier space, and etc. So you can have millions of those. And then you feed it into the equation, you see what structures you get. And usually we can get maybe a dozen. And then you can also think about it the other way, which is that you can design structure. You can say, this funny structure I'm interested in, which could be a possible phase. You can just construct the structure by hand, and then you feed it into the equation. And if it converges to some structure, it is a solution. I mean, that's the beauty about this. Like say, mathematically, we don't have a proof saying that those solutions exist or not. But practically, if we find a solution, it is a solution no matter how we find it. So that's the stage if we want to discover it. And we actually wrote a paper in 2012 where we considered an ABC star Copolymer, and we use this, we get about 50 or so structures, and only about 7 of those can become equilibrium phases. Most of them are metal stable structures, but the idea is that it's possible to do that. Although, like I said, we can never claim, say, we exhausted all possibility, no one can. But so that's one way. The other use, which is what I'm going to use lots here, is that we are restricted to say 15, 20 candidate structures, and we want to construct a phase diagram containing these structures. And that's easier in the sense that we can just use this initial condition of these correspond to these different structures, and we feed it to the equation, we find the solutions, and then we generate the free energy curve. And this is an illustration of that, which we consider a multi-block copolymer like this. And the red and the blue would form spheres. So these correspond to the binary ionic crystal. You have 2 types of spheres. They can form certain structure. And then the question here is that what structure they would form. And so, this is not what I'm focused here, but I just use this to illustrate the theory. So then what we do is we use this as possible structures. These are, of course, from textbook. You have, say, system chloride, sodium chloride. This is just simple cubic, body center cubic alternating spheres, simple cubic alternating spheres, etc. And we use this as the initial condition for a given set of parameters. We can generate a free energy curve like this. And then from there, then you know, if you change the volume fraction of the tail green block, you can drive the system from silicon chloride to sodium chloride to zinc sulfide. So that's the way we do the calculation. Now, with this, then we can construct the phase diagram. Now let me go back. We can construct the phase diagram. So this is the phase diagram which Greg showed, and which for simple diblock copolymer. Now the good thing here is that, the interesting thing here is that this would be the phase diagram you see for many years before. The idea is that it's lamella, double gyroid, and hexagonal cylinder, body center cubic, and cross-packed spheres. It is very simple. Now, what's not being realized is that the conformational asymmetry, the difference between the two blocks is an important parameter, and that's actually, as Greg mentioned, is an enabling factor to form different phases. And this would be a phase diagram where if the two blocks are different in coolness here, then it opens up the gap here where you can have the front cut for sigma phase and A15 phase. And again, this is something anticipated by Greg many years ago before experimental observation. And also why this structure form. Correct. Mentioned that. I'm not going to talk about that. Yeah. Okay, maybe I talk about this. So this one is really after the experiment found the Frank Casper phase. Then this is what actually Wei-Hua Li, my collaborator, and his student did his phase diagram, which shows that the Frank Casper phase could appear. And then there's later experiments showing this mechanism is working. From experiment, you can have systems with different conformational asymmetry from about 1 to larger than 1. And that's roughly corresponds to the experiment, but not quite, in the sense that from the theory, from the self-constant field theory, if you look at this phase diagram here, the conformational asymmetry number is 3. This is quite large. And in the experiment, the larger one here is 1.7. So from the self-constant field theory calculation, we need a conformational asymmetry, which say about 2, is 1.8, to have a window of sigma phase open up. But experimentally 1.3, you already have a size for sigma phase. So there's some description, so qualitatively it's here, is the conformational asymmetry makes that phase appear, but quantitatively there's a discrepancy. And this discrepancy, there are many reasons. And one reason we thought was actually the polydispersity in the system. The idea here is that all these polymers are synthetic polymers, and all synthetic polymers are polydispersed. There's not very, very rarely people can synthesize polymers over the same length all the time. So that's actually my former student Tom Lay did the calculation, which we say, okay, let's consider conformational asymmetry, and we made we have two conclusions from the conformational asymmetry study, which I'm not going to talk in detail here, but I'd like to mention. If you have proper conformational asymmetry, the phase diagram will look like this. That is to say, you can have the very sizable sigma phase. You can also have this Lewis phase pops up. Lewis phase are another set of complex packing phases. The difference is that the volume difference of the different domains are much larger. So it's much harder to form a monodispersed system. But once you have different components, you can have. So I think probably what I want to bring up with this is the importance of different species. So that then leads to my next. Oh, okay. I'm not going to mention this. This is just saying that actually, Greg, you predicted the branched one would form from Casper faces, and these are two experiments saying, yeah. So instead of that, what I like to mention here is that if we summarize this, the formation of this from Casper faces, you can change the conformational asymmetry. That's what we've been talking about. You can also use different components. That's what I alluded to by saying that this polydispersed system. Now, it turns out that you can use blends. And this is an illustration of two blends. So let me just, this, okay. This is kind of like a summary. This is a figure we made up trying to illustrate the idea. The idea is that if you just have one dipole copolymer, you can form these faces by changing the conformational asymmetry. But once you mix another dipole copolymer, the same chemistry, but different block length, then you can introduce more faces. So that's the basic idea. Now, the mechanism is actually quite simple. The mechanism is that when you add a second component into your system, the second component can, well, there are three ways. One is that they don't mix. And the other is that they go into the middle of the domain. If they go into the middle of the domain, they'll act as filler. And what they do is, if there's a void, they go to the voids. Now the other chains don't have to stretch. So that will relieve the packing frustration. So that's one mechanism. But that's not all. If that's so, then the idea is that why don't you just add homopolymer? Or like in surfactant solution, you have water, which goes everywhere. So that's that mechanism, which works, but it's not the complete story. The other story is that because the added component is also a block copolymer, so they would align with the domain, and if they do that, they would go into the interface. And when you have things at the interface, they'll act as what I call it co-surfactants, which is basically they're going to modify the interfacial properties. And the interfacial properties are really two things. One is the interfacial energy, so they lower the interfacial energy. But more importantly, they're going to change the spontaneous curvature of the interface. So these two will then lead to the mechanisms which make the blending strategy useful. So that's the sort of basic idea. And actually, Jai and I just published a feature article reviewing this part in Longmill, if you're interested. Now, again, starting the binary blend of copolymer is not a new topic at all. If you look at the literature, Professor Hashimoto probably have 50 papers published in macromoleculars. The title is binary blend of copolymers 1 until binary blend of copolymers 15. I'm not joking. They are there if you look at that. So he basically used small angle X-ray scattering study. And the lesson we learned from this previous study are two. One is that adding block copolymers, you introduce this macrophase separation into the system. That is the fourth thing is that they don't want to mix it. That's a good possibility. So you would have very large regions of two phases. I can see from this phase diagram here. Well, that's the theoretical phase diagram is always better. So let's say these are two phase regions. So that's one. But what's actually more interesting is that Hashimoto observed that if you mix two block copolymers in together, they could form a structure which are not the parent ones. And the particular case is showing, again, let me use the experimental one, which is that I have a lamella forming block copolymer on this side, another lamella forming on the other side. If you mix them together, you form cylinders. So that's actually a piece of information which is very, very interesting. Now, again, the reason here is very simple, is that the question I usually ask is that you have a block copolymer, so diblock copolymer. The volume fraction is 50-50. The interfacial curvature is spontaneous curvature is 0. It forms lamella. Everybody's happy. But once you change the volume fraction away from 50-50, the interface immediately acquires a spontaneous curvature. Then the question is, why you don't form a very big cylinder or very big sphere? And the question here is, of course, the interface would like to do that, to have a constant curvature, but the packing or the chain is unhappy because you have this stretching. Now, the idea is that once I have two type of block here. One is, say, perfectly symmetric. The other is a little bit unsymmetric, but with different lengths. And now you have that radial segregation, which release this packing frustration. And once the packing frustration becomes a non-issue, then the interfacial curvature wins. And now you have the cylinders. So that's why. So it's when you think about it, it's really natural to think. Now with this, then that's actually we decided to that's after the observation of these front Casper faces. Now we decided to say, why don't we try to mix in another diblock? Okay, here my other diblock copolymer got hidden here. Why don't we mix another diblock copolymer into a diblock copolymer and to see what happens? Now, well, there's another diblock here, and what this phase diagram shows is that if you just have the first diblock, it forms body center cubic phase as the equilibrium phase. Now, if you add the other one, this axis is the length ratio of the added one to the native one. And if this becomes longer enough, it opens up this window for the front Casper faces. Not only you can have the sigma phase, A15 phase, you have the C14 and C15 phases. So this was actually, we were quite surprised to see this. And this is a more complete phase diagram we constructed here. Now this axis is KN or temperature, and this is the added diblock. And you can see it can, I mean, this is the lamina forming here, and this one, it depends on temperature. It can form BCC, can form a hexagonal phase. The idea is that if you just go to one horizontal line, that's a constant temperature, you mix different copolymer in, it can go through these phases. So that's, of course, something we thought theoretically is there. Does it work? Now it turns out it does. There's some. There are two sets of experiments. This is from base experiment. This is from Yamamoto in Nagoya, and they basically did this recipe. And what it shows is that indeed, if you add these two block copolymers together, this is the X-ray scattering showing the evidence of the different phases, and this is the experimentally constructed phase diagram. I would say, I mean, there are lots of things we don't have in our theoretical phase diagram. For example, we don't have the quasicrystals. And the quasicrystal, I think Simon who mentioned the quasicrystals last time, it's actually a very interesting topic to me. Like, say, can we stabilize a quasicrystal using block copolymers? I don't think that we have a definitive answer yet. But on the other hand, beside these, like I said, the dense liquid phase, quasi-crystal phase, I would think if you draw a line from our phase diagram and this phase diagram, at least the sequence of phases is roughly there. But at least it says that mixing is a strategy which works. Now, then the question is why? Like I say, why binary mixture works that way? And of course, as I alluded to, the idea here is that there's two mechanisms. One is the segregation to the domain, and then another is at the interface. Now, this let me talk about this. So first of all, this figure here, what we did is that we constructed the domain, what you call it, the weakness cell of your structure, and then we calculate how much the added copolymer, which is the longer one, in there, and the amount, of course, would correspond to roughly the size of that domain. And we plotted that we did that for all phases. We considered from the simple BCC to the A15 to the sigma phase. And what we see here is that indeed there's a segregation of these second component. Roughly, this curve is divided into these 4 groups corresponding to the flank polyhedra of the weakness cell. And the one interesting observation here, by the way, this is the amount of second component we are in. This is how much in that cell. If they're all uniformly distributed, would be this dashed line. But of course, there's a segregation. There's less amount in the smallest domain, and another amazing thing is that this amount doesn't depend on which structure it is. It only depends on the coordination number. So this is CN412. And then you go up. Like say, this one is the 16, which is the largest domain. So, or in another word, indeed, it is the segregation of the second component, which regulate the size so that the system is easier to form spheres of larger size and smaller size. Now they are more, it doesn't cost you much energy to do that, and they'll be able to pack into these different phases. So that's one way. And the other interesting part is that the distribution of these second components. Now that's shown in this figure here, which is basically showing the second component, how they distributed at the interface of the core of the ABE interface. And again, the idea is that you have a differential distribution. Oh, well, there are two things here. One is that you have a differential distribution, and also the longer one would go into the domain to make to relieve the stretching thing, stretching frustration. And also, if you look at the curvature of this core interface, and they corresponding to the junction of the two components. That is to say, you would have the longer ones, which focus at this point where you have the smaller curvature. Now you have longer ones on this side, shorter ones on the other side. So you make that that happen. So this is really illustrated the two mechanisms I mentioned, which is that it acts as a filler to regulate the size, and also it acts as the co-surfactant to regulate the interfacial property, so that it's easier to form non-spherical, spherically shaped core. Now, this mechanism works not only for the spherical domains, it works for the continuous phases as well. And this is a little paper Tom and I published, which is that we were actually asking the question that for dipole copolymers, only the double gyroid was the equilibrium phase, and the double diamond and the promised nightmare phase were not. And we wonder, first of all, we kind of like understand why, because when you have more arms coming out, then you have larger space in there, it's harder to stretch things. That's sort of like our naive argument. And then there were calculations, actually Masson did and others did calculations, say if we throw in some homopolymers, which would go into the nodes, and that will relieve the frustration there, and that may open up a window for the double diamond. And indeed, his theoretical phase diagram showed that works. So that's great. But then we were thinking about that's probably not more, because if you look at the interfacial curvature of this animal, you have this part, which basically is a tube. If I call this positive curvature, then this node, the curvature are completely wrong. So it's actually amazing that they actually form it, because the interfacial curvature they're not very they're very uncomfortable in that region. So then we were thinking about, can we use another dipole copolymer, which will act as dual of function, filling the node and also modify the interfacial curvature. And the idea is that we use something we call it almost homopolymer-like dipole, which is that we take one and with a tiny bit of A, and with that strategy, we have a phase diagram like this, which shows that if you start with a gyroid forming one, if you add this almost homopolymer-like dipole, you can stabilize the double diamond, and you can also stabilize the promised nightmare phase if everything is doing correct. And again, I mean, these are theoretical predictions at the moment, and I hope people try to see whether it can be verified, proved or disproved experimentally.
Question.
Yeah.
So the reason why almost homopolymer is because some of them are going inside and some are sitting at the
That's right.
interface.
It's right here. That's right.
That's it, right?
Yeah, some of them will go inside because you still need to swell the node to relieve the packing frustration. That's the major part. But you also want to relieve the frustration at the wrong interface part. And that almost homopolymer like copolymer would go in here. Then it has a very long tail in on that side and the short one on this side, and it kind of reverses the interfacial curvature.
And then I recall there's an observation, I think it's Hashimoto 3D reconstruction of I think that in a blend.
Yeah, well,
Or is it 3 chains?
it's a homopolymer chain. Experimentally, as far as I know.
I'll look and see.
Yeah. I don't remember Hashimoto has it, but yeah. All right, good. Any other questions? All right, so that's how much time? All right, so there's more interesting things that I'd like to mention, and this is again. This is the continuation of the AB and AB homopolymer, AB and AB dipole copolymer blends. What I showed was a phase diagram around below that. Now the question is that if you keep increasing the length of this A, what's going to happen? And this is actually Wei Hua Li's work from Fudan University, not my work, but I think it's quite interesting. The idea is that if you make this A block, the length difference too big, then they would decide they are not comfortable mixing together. They would like to separate. And when they separate, they still form a spherical domain. Now, what you have is you have larger and smaller spheres mixing together. And what they found is that the large spheres form a regular lattice, BCC, or whatever phase center cubic in here, and then the smaller spheres would fill the gap, the voids, And then they'll find a comfortable structure to form these. And I don't know whether that's useful or not, but that's really another interesting thing to think, which is that you can still mixing things and you form different objects, and they organized pack together to form a larger ordered face. And that's, of course, another interesting thing to we can think about. Let's see here. Oh, okay. So I mentioned a lot about mixing diblock and diblock. It turns out that you can also do very simple thing by just mixing homopolymers into the system, and that can promote the formation of the front Casper faces as well. And this is this was actually observed experimentally first, again from front face group. And what they did is they simply added. You have a diblock copolymer, you added some homopolymers into the core. And it turns out that experimentally they found the phase diagram like this. And this is the theoretical phase diagram we constructed. Now here, you are really fighting against the macro phase separation. This is the full scale phase diagram. There's a huge window where they don't mix, you just have two phases. And the mixing region is only up to about not to 20%, about 15%. Then you can have these ordered phases appear. So it works, but there's a limit. Now again, this is. I'm not going to go through this. This is again showing the volume fraction and the size difference. It's really the mechanism here is regulating the size of these different domains. This is some stories. Okay, yeah, let me just talk about this. So this is another interesting thing, which is that when you do plans, what's interesting things going to happen? Now, this is something, let me see, what do I have here? Okay, let me just put this in. So the idea here is that I just talked about I'm using AB and then I'm mixing A, I form these phases. I just talked about. Now, the question here now is that if we are thinking about the multi-block copolymer, if I have an AB diblock, if I connect another same AB diblock to it, then from the volume fraction point of view, nothing changes. If I have, say, 50% red, 15% blue, I still have 15% red, 15% blue. The only difference is the limit. And that will make a little difference in the phase diagram, in the sense that this is the completely symmetric phase diagram, theoretically constructed. And this is where you connect them. You don't really see much difference. The difference is that it's slightly asymmetric because you connect AB. And you can also connect the other way. I can connect from ABA like these, or I can connect the other way. And these are, of course, all homogeneous. Is that the way it works? Polymers, which means they have the same chemical composition, but different topology. And the idea is whether there be any difference in their phase behavior. Now, it turns out that if we are thinking of the melt, that's the ABA. If I flip the ABA and put them together, you don't really see much difference there about this tiny difference. The question we are interested in is that if we mix AB plus A, we form this phase diagram. Whether now, if I have ABA or BAB, which chemically should be the same, and just a tiny difference, now I mix A in. How much difference do I see? So that's actually the question we are interested in, which really is a detailed thing. Now, the idea now is that now I'm mixing A to ABA. That's the phase diagram. This is of course already quite interesting. But now if I connect the longer one to form ABA, I mix A in, and this is the theoretical phase diagram. There's really not much difference. The only difference is this boundary moved a little bit over. Otherwise, the topology is quite similar, almost all the same. Now, if we decide to connect the AB diagram the other way to form BAB, and look at the phase diagram, there's a huge difference. And we were really, really surprised by this, which is that the only thing we changed is that we just take this guy, we link them to the red part or link them to the blue part. And this really shows that the topology of the blocks, which are very, which are important. Now, the question is, of course, is why that's so. And the idea is really that there's a difference in the mixing or in the miscibility of the A homopolymer, depend on whether the A in the domain is free or the A is linked in there. So that there's a difference in that, and that's what we and also the other thing, I mean, this is okay for the physicists here now. We find is that it turns out that the simple change of the architecture of this leads to a qualitative change in the behavior in terms of the so-called Lipschitz point. Now, what it is that now let's imagine we have a mixture of a dipole copolymer and homopolymer. If you have all homopolymer, it's a phase-separated system. If you have dipole copolymer, it's a microphase separate system. And if you keep mixing homopolymer in, at some point, it will phase separate. And the point separating these two behaviors is something called Lipschitz point. And that's which are these points. Now, the Lipschitz point technically is the instability point of a homogeneous phase. If you have a homogeneous phase and you make a fluctuation and you ask the question, what is the free energy cost of this fluctuation? And if that free energy cost is 0, the system becomes unstable. If it's negative, it's just completely unstable. And that and the wave vector of this fluctuation, where the instability occurs, is the quantity which we use to indicate this Lipschitz point. If this Q, the wave vector, is non-zero, then you have microphase separation because the instability is against especially varying wave. If Q is 0, then you have macrophase separation. So that's how we do that. So then it turns out that if we plot the free energy cost, and technically this is the random phase approximation coefficient, as a function of Q, the wave vector, okay, you will see in this case, there's one minimum, and this minimum moves to 0 continuously. But in this case, you have one minimum, you have another minimum. Or in other words, if I plot the Q value at 0, at the instability point, in first case, it goes continuous to 0, and in second case, it goes discontinuous to 0. So it looks like there's a qualitative difference when you do this. And that's something I found quite interesting. I think.
Wait, you want 10 minutes of questions?
Oh, okay.
How you want to take the last 10 minutes?
Okay, I think probably I just let me take questions instead of going on, because there's lots of variations here I can think. For example, I can think about instead of AB and AB, I can have AB and CD. And if I make B and D attractive, then I can have different spheres or different sphere, cylindrical sphere, and lamella, and they can all mix to form different phases. Now we really get into very complex cases. So I just leave it here, and this is wide open area of research now. instead I take questions.
Oh, thank you very much.
Really interesting. So when you blend, I understand that you put all the components in at once in a mixture, but you could imagine you take one of the components first and then you titrate in the other component. And surely that should change the behavior because the first one starts to assemble and the other one then has to work with that. Can you comment on what you expect there?
Yeah, yes, I can. And this is a very interesting question you brought up. All the phases phase diagrams I constructed are for equilibrium phases, and by the nature of that, they should not depend on how you prepare them. So that said, but the question you mentioned is that remember, I showed the free energy landscape, and there are lots of local minima. So there's there's 100% possibility that if you do different ways of processing, you're going to get into different local minima. And that's a very, very interesting topic, which is that if there's a particular phase we want, and which is not a global minima, but a local minima, how can we prepare the system to obtain that? That's a very, very interesting research topic in our community. Yeah.
Yeah, question on this last point on the Richard's point. So in the first case, on the top there, that sort of suggests that periodicity is going to have a wavelength that's getting larger and larger as we approach.
That's right. It's kind of like unbinding, right? More.
Yeah, so what's surprising, of course, is that it's a wavelength that's getting arbitrarily big compared to the size.
That's
of the
right.
molecule.
That's right. Yeah, that's right.
Perhaps it's probably unstable.
Yeah,
Fluctuation.
yeah, absolutely, absolutely. This is just from the very simple RPM analysis, and it just pops up like this.
Any intuition?
No.
You have any intuition?
No, we just got this. Yeah.
Thanks very much. So you had that phase diagram of dye blocks plus monomer, plus individual monomers, where you found the diamond surface and then also the feed surface. And I think you found the diamond surface at higher interaction,
Yeah,
the greater segregation than the primitive surface.
that's right.
Have you got an intuition why that is?
No, I can't. No, you intuitively, it's very, yeah, no.
That's sort of because Philip Schoenhofer, he did a simulation a while ago on this pear-shaped system where he then added spheres to the gyroid, and he was able to stabilize at least to a degree the diamond surface. And he found the same thing that you find, which is that the individual spheres don't go only to fill the gaps.
Yeah, it goes.
They actually sit kind of in the membrane to alleviate frustration. But I still can't understand why you would get the free surface at lower.
I mean, I guess I would guess, maybe tell me this is wrong. You have some population where that A chain is so small that it just pulls it down into the region.
That's right. That's right.
These interactions, the sort of distribution, ones at the interface, and the ones sort of in the volume are being modulated.
But the need to alleviate curvature breastbone will be presumably similar in PMV.
Well, can we say that the curvature, the wrong curvature is more severe in the gyroid than in the premier phase because you have more nodes? I don't know. Maybe you.
I don't personally subscribe to the curvature picture anyway, but for these systems, but going to what you said previously is if you took A and B and then you add just A, you can get G.
You can get G to DD. Mhm.
And you can also do P as well, if you put more in.
Yeah,
For
but
certain-
that don't go in, then you have phase separation. Right,
Excavator has at least a phase diagram with a couple.
oh, yeah, that it's,
If that's true, and you can think that these ones are sometimes acting like. Some is doing both, something in the interior and something.
yeah.
I find I feel like there's two ways, you're saying both ways of doing the same thing. I find it's kind of hard to separate it.
But if you were to go by that picture where you need to fill in the gaps, in addition to the relieving curvature frustration, then of course you would expect P, D, G, in that order.
And the function of what?
Well, as a function of one of our addition.
Yeah,
G doesn't need any additional monomer, D would need a little bit of additional monomer, and P would need a lot.
Yeah, I think that's right. I don't know what path.
Anyway, that's
It's
fascinating.
definitely doing something.
yeah.
And I guess the question, what is the G that you get, what's the difference between the re-entering shower phase you get up there? So you keep going,
Yeah,
what's this difference in structure?
I have, yeah, I can, it is,
Okay, I'd be interested just to pull it up.
I can, it's in our paper, but,
Yeah.
Okay, let's think Professor Shi once again.
All right.